This is a delightful, quiet stroll through Problem 2 of Practice Exam 1 in Module 12 from the book Problem Solving Guide for Mechanics and Thermodynamics. We have 4 different procedures here. We have to get the change in internal energy, the thermal energy delivered to or from the gas, and the work done by the gas. So the initial condition is the same. 2 moles monatomic gas in a 50-liter container at 500 kelvins. That's a starting point for each of the 4 procedures. The first procedure, cooled to 300 at constant volume. The second procedure, cooled to 300 at constant pressure. The third procedure, cooled to 400 at constant pressure and then cooled to 300 at constant volume. Number 4, 2,500 joules is removed at constant volume and then heated back to 500 at constant pressure. The internal energy of a monatomic ideal gas is only a function of its temperature. The function is 3/2 nRT. There's no pressure, no volume in there. Any change in internal energy must be a result of a change in temperature. If the temperature doesn't change, the internal energy doesn't change. We know the final temperatures of all 4 procedures. We know the initial temperature. We can get delta E internal for all 4 states right off the bat. So it went from 500 to 300. Delta T is minus 200 kelvins. It's always 2 moles. That's the gas constant. So for procedure number 1, when it went from 500 to 300, delta E internal is minus 5,000 joules. Procedure number 2 has the same final temperature. Delta E internal is also minus 5,000 joules. Procedure number 3, same thing. Drop 200 kelvins. Delta E internal for 2 moles is minus 5,000 joules. Number 4, it ends at 500. So the internal energy change is 0. Starts at 500, ends at 500 kelvins. So let's put these in the table. And we feel like we're making progress right now. We got all the delta E internals. Now let's think about the work done. In procedure number 1, no work is done. The volume is constant. Let's put that in the table. 0 joules for the work done. If the energy dropped by 5,000 joules and there's no work done, the volume didn't change, Q has to be negative 5,000. That's the only way the energy is going to drop by 5,000. You took 5,000 joules out. You stuck it in an ice bath. You sucked 5,000 joules out at constant volume. In procedure number 2, work is being done on the gas. It's P delta V. The initial pressure of the gas, we can use PV is equal to nRT. So 2 moles, there's the gas constant, the temperature is 500, and the volume is 50 liters. Convert that to cubic meters, and we get nothing's happening here. We're just calculating the pressure of the first state, the initial state. It's the same for everybody. Everybody starts in the same state. So that's the initial pressure for all 4 procedures. So now the final volume, we have to go to 300 kelvins. Same pressure, right? It's constant pressure. This is procedure number 2, but now we're at 300 kelvins. So the volume, not surprisingly, drops by 3/5. It was 50 liters, now it's 30 liters, 0.03 cubic meters. So the work done by the gas is the change in volume. It went from, times the pressure, it went from 50 to 30, minus 0.02 cubic meters. There's the pressure. And we multiply these to get the work done, minus 3,330 joules. So we put that in the table. Now we got to think. Let's not use equations. Let's think. What the heck is Q for this process? We're trying to cool the gas down from 500 to 300. So we take our gas, let's assume it's in some kind of a metal container with a piston, and we stick it in an ice bath or something, and thermal energy is being transferred out. But while the thermal energy is being transferred out, the piston's coming in. the volume is shrinking because the pressure is constant. We're cooling it off. The only way the pressure can remain constant is if the volume shrinks. So when the walls come in, the piston comes in, they're hitting the gas molecules. They're giving them energy. They're doing work on the gas. This W is the work done by the gas, which is negative. So 3,330 joules of work is being done on the gas while it's being cooled by the piston. How much energy do I have to take out? We have to get it all the way down to 300 while 3,330 joules are being put into the gas. I've got to leave it in the ice a lot longer. So delta Q is minus 8,330. We got to do both of these. All right, let's put it on the table. Number 3 is 2 steps. First, cool at constant pressure to 400. Let's think about that. There's work done here. It's constant pressure. The volume's changing. We need the volume at 400. So we put in the temperature of 400. We know the initial pressure. We calculated that already. And not surprisingly, it's 4/5. The temperature is 4/5 of what it was. If it's constant pressure, the volume is going to be 4/5 of what it was. So it went from 50 liters to 40 liters. That's a change of minus 10 liters, which is minus 0.01. So there's the pressure. There's the change in volume. That's the work done. We can put that in the table. Oh, let's not put it in the table yet because we have to think about 400 to 300. So this is for the entire transition, the entire procedure, number 3. No work is done from 400 to 300. It's constant volume. So the total work done in the 2 steps is just the work done in the first step, which is minus 1660. And now we can put that in the table. This means that plus 1660 of work was done on the gas. So Q has to be minus 6,660. You have to take energy out to reduce the temperature and take energy out because work is being done on the gas while you're trying to cool it off. All right, number 4. Procedure 4 contains 2 steps. The first step is 2,500 joules is removed at constant volume. Then it is heated back to 500 kelvins at constant pressure. Let's take these one step at a time. The gas is first cooled by removing 2,500 joules. Cooled by removing 2,500 joules means we took out 2,500 joules by cooling it, which means Q is minus 2,500 joules. The volume didn't change, so the work done is 0. So delta E internal must be minus 2,500 joules. The only way to reduce the internal energy of an ideal monatomic gas by 2,500 joules when no work is done is to take 2,500 joules out. The temperature change can be calculated because we know how delta E internal is related to delta T for an ideal monatomic gas. It's 3/2 nR delta T. If you take 2,500 joules out of 2 moles of an ideal monatomic gas, its temperature drops by 100.2 kelvins. Started at 500 kelvins, dropped by 100.2 kelvins. The temperature now is 399.8 kelvins, and the volume is the same, 50 liters, because this stage is constant volume. The second stage is heating it back to 500 at constant pressure. So now we're ready to tackle the second stage, but we need the pressure at the start of the second stage, which is constant during the whole stage. We know the volume is 50 liters, but the temperature is 399.8. So we need the pressure at this volume at this temperature, and we can use PV is equal to nRT. And we get 133,000 newtons per square meter. And we need the final volume. So now the final volume, the pressure is the same, but now the temperature is back to 500. Again, we use PV is equal to nRT, this time solving for V. The temperature is 500, and the constant pressure during this step is 133,000 newtons per square meter, and we get 62.5 liters, 0.0625 cubic meters. Started at 50 liters, went up to 62.5 liters. The change is plus 12.5 liters, which is plus 0.0125 cubic meters. Work is done only during the heating phase because that's when the pressure is changing. There's no work done during the first step because it's at constant volume. The work done is P delta V. There's the pressure. There's the change in volume, 12.5 liters. It's positive. So the work done by the gas is plus 1660 joules. We can put that in the table. Now we can think about Q. There's no change in internal energy. The gas's internal energy did not change. It did 1660 joules of work. Where did this work come from? There's only one place it can come from, and that's from adding internal energy through the walls of the container by heating it. So that's plus 1660. So we've got the answers, but let's do a really deep dive into this problem. This problem is very complicated. Let's start with procedure number 4, looking at one stage at a time. There's 2 steps. So now we're going to calculate E, Q, and W for each step. We already calculated it. So here's step 1. It's given that we took out 2,500 joules. There's no work done. Delta E internal has to be minus 2,500 joules. In the second step, we're heating up back to 500 kelvins. And we're doing work. So we have to put in Q to do both of those. We have to get back up to 500. That costs 2,500 joules. And we have to do 1,660 joules of work. So the thermal energy we have to add through the walls of the container is plus 4160. So now we can look at step the delta E internal total is 0, minus 2,500 plus 2,500. That's what's in the table. Q during the first step is minus 2,500. During the second step, it's plus 4160. That's a net of plus 1660. No work done during the first step, plus 1660 done in the second step. That is plus 1660. So it looks like we're all set there. Now, let's look at the PV diagrams for each of the 4 procedures so we can really try to understand what's going on here. That's the goal, complete fundamental understanding. The pressure started at 166,300 newtons per square meter right here at 50 liters. The first procedure cooled to 300 at constant volume, so it's going to go straight down. That's 500 kelvins, that's 300 kelvins, no work is done. Let's look at the isotherms. Isotherms are lines of constant temperature. So here they are. The red line is 500 kelvins, the green line is 400 kelvins, the blue line is 300 kelvins. So this one went from 500 kelvins to 300 kelvins, constant volume. The second procedure starts in the same place, but it goes to 300 at constant pressure. If the pressure is constant, the volume is going to be dropping. So it starts in the same place, goes this way. It goes from 500 to 300 horizontally. We can look at the isotherms. They're the same ones, 500, 400, 300. So instead of going straight down, which is constant volume, it went to 300 at constant pressure. We can calculate the work done, we know the volume change, we know the pressure, we can calculate delta E internal, Q, and W. Procedure number 3, we start out at 500, same place. We go to 400 at constant pressure, then we drop straight down 300 at constant volume. So that's what this looks like. 500, 400, 300, and we look at the isotherms, and we can see it all makes sense. Work is done during this step, not that step. If we know P delta V, we can calculate the work done. And then we can get Q and delta E internal. The last procedure is a little bit different. We take out 2,500 joules at constant volume, so it's going to drop straight down. Then we heat it back up to 500 at constant pressure, which means it's going to go to the right. We're going back to 500. So that's this procedure. Starting at the same point, taking out 2,500 joules at constant volume, heating it back up to 500 kelvins. So there are the isotherms there, and hopefully it's all making sense. Hopefully you can wrap your head around these very difficult concepts. Hopefully the wheels are turning and you say, yeah, I think I'm starting to understand what's going on here, which means do some more problems. That's problem 2.